Yeah. So actually what we did earlier, we'll be just coding them that into an algorithmic form. So I'll just mention the book that I'm following. So in that book, written by Bradco, it is, I think, one of the famous books related to Prolog. So there the algorithm is written in a bit elaborate form. I have tried to make it bit concise for the discussion in the class. So, but the essence of the things I think I have captured more or less in a truthful manner. So the steps that we have done earlier will be exactly following this. So as you see that we have this function execute, right? By the way, am I audible?
Yes, sir.
Okay.
Yes, sir.
Okay, so the input to this is the program, and you know the program is the collection of rules and the facts, right? And the list of goals, right? And what it returns either failure, or if it returns success, it also returns the instances or instantiations for which we have got success. So this instantiation is basically the list of substitutions, right? So as you have mentioned earlier that if the goal list is empty, then we return true. And up till that point, whatever instantiation that we have got will be returning that instantiation, right? If the goal list is not empty, what we will do, we will take the head of the goal list. So let me take an example. So the example is say, so I'll just say ANC, it stands for ancestor, right? And we have got say Minsky, Russell. Hello. And you have got, so this is the goal I am trying to prove. Uh, is anyone trying to say something? Okay. So this is the goal. You can see that this is not a single goal. We have got a composite goal. So as we have this, we can have also a semicolon here. We can also prove this or those that, right? So what we'll be doing, we'll be pushing, we'll be taking the head of this, right? And putting that in the goal, in our goal. So in our goal, what we'll be having? We'll be having NC, M, R. And in other goals, we'll be having ANC, DC, right? And we start with satisfied false, and we'll keep on doing this repeated. So this part is basically repeated use of resolution rule, right? And for the condition, for that the condition is the goal is not satisfied, and you have got more clause in the program which can be applicable, right? So we select a clause which is of the form H to B1 to Bn, right? And we create an instance of this clause because I don't want to disturb this clause. So I'm just taking out another variation of this clause, right? Now, the first thing that we'll be doing, I'll be trying to check the head of this with whatever we have in our goal. So in our goal, what we have got one single goal. So we try to match this. So if the match is okay, then we have got the instance, and instance is what? Instance is basically a set of substitutions, right? Now, if we have a match, then we create new goals. So what are our new goals? So we are adding the newly this body part in the goal list. We append that before the other goals, right? So we add this, the body part, which is our B1 prime to say Bn prime, and add that to the list of other goals, but it should be appearing before the other goals because I have to prove this because we have started with this goal. Let us prove this, then we'll be going for the other goals. The next thing that we'll be doing is to substitute what we have got, right? So what we have in the rule, we have got ancestor xz is say advisor xz, right? So we have a match with this, right? So we'll be pushing this advisor xz here, right? So this will be our advisor xz, right? So the revised other goals, the new goals. Now we'll be doing the substitution. So what would be our substitution? We have M and R. So we are substituting X by R and Z by, sorry, X by M, Z by R, right? And if we have a success in this path, then this would become an answer, right? Now we have got a new goal list. Then what we do, we run the execute program with executing the program or execute function with the program that we have that is already fixed and with a set of new goals because our goal have been revised. And again, from that, we are getting this satisfied and instance. And we'll be doing this repeatedly until we have either we have a satisfaction or we have no other goals clauses to apply, right? So more or less, this is the way we execute the program. Now, one thing that I have mentioned while I was describing the Prolog program is that the Prolog program is executed or the rules are selected sequentially. So if you have the rules like say R1 followed by R2 to Rn, that is how you have written them in the file. So this rule will be tried first, then this rule, and then finally this rule, right? So let us look at a different reorganization of these rules, right? Not only that, we can have also ordering of the goals, right? So the question that we are trying to ask here, that whether reordering of clauses or goals have any effect in execution. So this is the question that we are trying to ask. And for that, we are doing an experiment. So the experiment goes like this. So this is my original version of the program. So the first thing that I'm doing a clause swap, right? So let us name this to be V1. So this is my V2. And here you can see I have not changed the rules, but we have changed the ordering of the rule, right? So our R2 has become R1 here and R1 has become R2 here. Now the third version here, we are keeping the ordering of the clause same as the original. But if you look at the last rule, here we have swapped the position of the subgoals, right? So this is the change that we have done here. And finally in V4, we have changed both the ordering of the clause and the goal, right? Now let us try to see whether we have any effect in the runtime. So the first one. So our goal is to prove whether ancestor, so Dana is an ancestor of Azizi, right? So this is what we have to prove, right? So for that, we'll be applying the first rule according to the V1. So we have the new goal to be advisor Dana Azizi. And in the fact, this is true that Dana is an advisor of Azizi. So that becomes true. Now, as this becomes true, the ancestor one Dana Azizi, this becomes true. My goal is satisfied. How many steps did we require? Merely 1 or 2 steps, right? Now let us look at the V2, where we have swapped the clause, right? So again, we start with ancestor Dana Azizi, right? I don't know whether the font is visible or not, but this is the best I could do because it's a very long list. So let me read it out if we don't able to say. So we are trying to prove ancestor Dana Azizi. So which rule will be applied first here? Can any one of you tell me? Hello? Pradeep, what do you think? Which rule from these two will be applied first?
R1.
R1, right. Now, if we apply R1, what we have here in our revised goal list, we have got advisor. We substitute X by Dana, and we do not have anything for Y. So what Prolog will do, it will assign one anonymous ID. For example, it has assigned, say, 46_4612. So whenever you have got under 6 something ID, that means it is not yet instantiated. So this is the semantic. So not instantiated. Right. And what is the next goal? The next goal is ancestor. Sorry. It will be Y, right? So Y is in our case 4612, and then Z will be Aziz, right? Now this is one anonymous variable. I can assign this with any value, right? So let me assign this with Felix, right? So we say advisor Dana Felix, and this is there in the knowledge base, so that's why this becomes true. Now, if this becomes true, then we have to substitute this with Felix. Now our new goal becomes ancestor Felix Azizi. Now again, which rule should we apply here? So I have to prove this. This is my new goal. Which rule should we apply?
R1.
R1. No, we will be applying R1 because this is a new recursion that we are starting. So it will be applying R1, right? So again, we have got advisor Felix, some new ID, say 4652, then ancestor 4652, then Azizi, right? Now Felix, if you go back and see, Felix did not advise anyone. So this becomes false. So whatever this value is, this becomes false. Now, if this becomes false, then what will happen? This entire thing will become false. So we have to backtrack, right? So we have to backtrack up to this point. Now, after backtracking, what we'll do now, we are repeating this goal. Now, which rule should we apply?
R2.
We'll be applying R2 here. Exactly. Thank you. Now, if you apply R2 here, what happens? It becomes false again because we'll be pushing advisor Felix Azizi. Now it will be doing lots of backtracking, but let me assure you that it will come with a success finally. But what is the price we are paying? We are unnecessarily repeating this, redoing the things, right? So you can see clearly that this is not efficient. So what we have done, we have just changed the ordering of the rule, and we have got a huge implication in the runtime of the program, the execution of the program, right? So let me talk about, I will not demonstrate what you can do. You can, the program is there in the example file itself. You can run it on your own, and you will see that for this program, so this is your V3. So what we have done in V3, we have swapped the goal here. So if you try to run this goal or try to satisfy this goal, for some cases it will give you quick solution, and in some cases it will go into infinite loop. And while you are doing this, both clause and goal swap, irrespective of what you do, you will be ending up with an infinite loop for this program, of course, but for other program it might have some other effect. So with this example, what I'm trying to convey, I'm convey these things. So what are the takeaways from this ordering exercise? The first takeaway is that just try to think about what did we do in the original version. So there we have presented the simple idea first. So if someone is an advisor of someone else, then they become ancestor, right? So that is the simplest idea. Then we went for the complex idea, and this is very much true for solving any practical problem. So this is a practical heuristics for any problem. You try the simplest idea first. If that does not work, then go for complex solution. I guess we do all this kind of thing in almost all the cases while you solve the problem, right? The second word of advice is that while you are ordering the clauses, don't do it randomly. So you need to trace your program to check whether there is any possibility of notorious infinite recursion. Right. So this is the second thing. Now, if you are saying that I'm doing ordering, what does that mean? I'm sequencing the instructions, right? So ordering means we are sequencing the instructions. But I promised you earlier that Prolog is a declarative language, right? I just declare the thing, then the thing is done. But here I revise my statement a little bit, that though Prolog is a declarative language, there is also a procedural aspect attached to it while you are talking about efficiency and decidability of the program. So we need to check the procedural aspect to ensure two things. One is either efficiency or the decidability. So if there is a solution, you will get the solution in limited bounded amount of time. That is what you need to ensure. And of course, you need to make your program more efficient by either reordering the clauses or reordering the goals. So these are the takeaways. So with this, let me just talk about some sample programs to warm up a little bit, then maybe go for some other programs that will illustrate the features. So as you can see that the first program that I have tried to capture is to print the number between the numbers between two numbers. So if you have say a range like 11, 10, 11, 12, 13, 15, 18, then 20, it will print 11, 12, 13, 15, 18, given you have a goal like this. So what do we have? We have got two numbers, N1 and N2. So these are the upper bound and the lower bound and the upper bound, right? So the first thing that we need to check, so let's say you have the base conditions like say 10, 10. Would you have anything to print? So there is nothing to be printed. If you have say 10, 11, there is nothing to be printed. Only point when we'll be starting to print is something like this. So we'll be then printing 11. Then I'll consider this list. So first I consider the entire list. Then after I have processed this, then I'll be considering this. Then considering this. So you can see we have a recursion, sense of recursion here, right? So first we check whether these things are happening or not. So if these things are not happening, then I'll be going into recursion, right? So then the first thing that we'll be doing, I'll be incrementing this n1 by 1 so that I can print it. So n is n plus 1, right? So now I'll like to illustrate one feature here. So this particular thing is called variable assignment. So traditionally in procedural languages, we have performed assignments like say n equal to n1 plus 1. So that is not really, that is allowed, of course, but that will not serve the purpose that we have at our hand, right? So instead what we'll be writing n is n1 plus 1. So what this will do, so let's say you started with n1 equal to 10. So what it will do, it will try to check whether n is equal to 10 plus 1, not n equal to 11. It will not do that. So it will assign this 10 plus 1 to n. For this evaluation and assignment, this thing you have to do. So you have to say n is n1 plus 1. So this is one thing that you need to consider, because this is kind of different than the procedural languages, right? So the next thing what we'll be doing, we'll be printing n. So this is for new line. Then the next thing will be going to the next part of the recursion, which is I'll be considering the list from 11 to 20, right? And for doing that, we have got this n1 to be n plus 1, and we call the program recursively, that is n1 nn1 to n2. So we are just calling this using this range, right? I hope this is pretty intuitive. So what you can do is see that we have not used the iteration, right? We have not used the for loop. So traditionally, what would we have written? We have used one for loop and then do this, right? But here we are not doing any for loop. We are just doing the recursion and our thing is done. And basically, if you think this can come with intuition also. Now, the next program that I like to talk about is sum of numbers in a range. So what we have, again, we have a list like say 10, 11, no, not a list. So you have got two numbers, 10 and 20. So you want to sum this, sum of the series, then it will be 10 plus 11 plus 12 plus then 20. So this is what we want, right? So here, if we have a single, if we have something like this, say sum 10, 10. So the sum will be 10. So this is our base condition. Right. Now, what is the recursive step? So we have this n1 and n2, and we want to retrieve the sum, right? So first we check whether this range makes sense or not. We increment n one by one, and then we call it recursively with n2, n2. So we have a list. We pick up the first one, which is n1, right? And we have the remaining of the series. And as we go, we compute the series. We are not storing them in a list. And we are storing the summation here in sum iter. And after we have computed this, finally, our sum becomes sum iter plus n1. And again, you see that this is again very intuitive, right? So the next feature that after recursion I like to talk about is the list data structure, right? Now, what is a list data structure? A list can either be empty, so this signifies empty list, or you can write a list like this: head, then followed by a tail. So an example would be, say, 1 followed by 2, 3, 4, 5. So this is basically equal to 1, 2, 3, 4, 5. So we are taking out the head element, and remaining part we are assigning to the variable tail, right? Or we can take out as many as elements from the front. For example, I can write the same list as, say, 1, 2, 3, then say 4, 5. Hello. So if we say this is others, and if you want to say, if you want to see that this is equal to, this is same as this list. So what would be others? Our others would be 4 and 5, right? So like we can have a flat list, we can have a nested list also. So this here we are providing an example of nested list or list inside list. So those we have written Python, you know that you can write list inside list. So we are defining two colors. So color one, maroon and green. So basically this is a combination of the colors for one of the greatest football clubs in Bengal, which is Mohun Bagan. And color 2 is for East Bengal. The color is red and yellow. Now I'm trying to define the list clubs. The first element is the name of the club or the club variable, then the colors, right? So this associates Mohun Bagan with colors and East Bengal with color 2, right? And if you print this, it will be like Mohun Bagan, then a list maroon green, East Bengal, then a list red yellow, right? So you can play with all these things using this ID. So as you play more, you will be you'll be seeing different kind of scenarios that may arise, right? So now let me take out some examples and try to demonstrate them so that we can learn the features as we go. So the first example that I like to take is concatenation of two lists, right? So let me give you the kind of design aspect, then we might go to the program and see how the program can be written, right? Now, whenever we are trying to frame anything using recursion, we have to specify two things. So this is the way you need to think while you are writing recursive Prolog programs or any recursive program, right? So first you need to specify the base step. So what is the idea? The idea is you have a list 1 and list 2. You want to concatenate these two to get L3, right? Visually, it will be L1 plus L2 equal to L1, L2, and this is basically L3, right? So can any one of you tell me what should be the base step?
empty list concatenate.
Hello. So empty list. Then. Hello.
So empty list with L1 will give L1 and L1 with empty list will give L1.
Okay. Empty list plus L1 will, or I can say L because we have got only one variable here, equal to L, and L plus empty equal to L. So how can we devise the recursive step? So I'll spend some time on this program. For the rest of the programs, I may go a bit faster. So what would be the recursive step? Or what should be the thought process for the recursive step?
Sir, we will first divide the L1 into a single element at first and then the rest of the list.
Okay. So how to do that? So you can say
X.
L1. Then
it will be list X concatenated with the function L1, L2, L3.
list X concatenated with
the recursive function.
List X concatenated with, then tell me. Yeah, so you have to write somehow in this form, right?
Yes, sir. Sir, I was telling that concatenation L1, L2, L3 will be in the function, and then list X will be with the plus sign. It will be there.
No, actually, plus sign does not mean concatenation, first place, right?
Okay.
So we cannot use plus sign here. So that if the plus sign was there like Python, then this concatenation program we did not have to write. Okay. So let me tell you the basic philosophy of writing this program, but there might be other ways to do the same as well. So what we'll be doing, as you mentioned, we'll be picking up one element at a time from the first list. So X from the L1, right? And we will be putting that in the output list, right? So let me first draw it, then I can explain. So this is your first list. I can represent the first list like this, right? Now we have the second list L2. I have to come up with the third list. I have to come up with the third list. So what would be the, so this is the output list, right? So what would be the first element of this list? If we have a situation like this,
X.
X. And what would be the kind of property of this? The remaining part, if we just name it L3. What would, yeah,
Concatenate L1, L2, L3.
exactly. So if we can somehow concatenate L1, L2 to give us L3, then we have solved the problem, right? And you see, this will go into the recursion, and then L1 will be divided as X L1 prime, and we'll be keeping on doing that until we reach the base condition, right? Now at this point, tell me or argue whether two base conditions that we have specified earlier both are required if we use this philosophy.
The second one is not required.
Second one is not required. So though it will not cause any harm, but the first one will do. Right? So now we have got all the ingredients to write the program. So let us first write the base step. Concatenation empty list with L give us L, right? Then concatenation, how do we write the second thing? I know our first list, right? So X L1. So this is our first list, right? So what is the second list? L2. What we want to achieve? We want to achieve X L3, right? So in order to make it to be true, what are the things that we need to make true? So you need to make this conc L1, L2, L3 to be true. Does that make sense?
Yes, sir.
Good, good. So the program version of this, if you go into series some is there. Yeah. So let us try to run it for the sake of demonstration. So what we can write, say 1, 2, 3, 4, then say 5, 6, 7, 8, and you want to store that in L. So as you expected, it will be creating a list. Or let us do a bit differently. So let's say we have something like this, say 1, 2, 3, 4, 5, 6, 7, 8. And we know the second part of the list, but we don't know the first part of the list. The question I'm asking here, that which list, if concatenated with 5, 6, 7, 8, will give us this entire list, right? So you can see that here we can ask whether the goal is satisfied, or we can ask the value of the variable in order to satisfy the goal. So you can see that we have got this L1 to be 1, 2, 3, 4, right? So this will be useful in many programs that we'll be writing later, right? So similarly, in order to test the membership of an element in the list, so the base step would be like, if we have, this is the element that I want to check, and if you see that X is there in the first position, I don't care what is there in the remaining in the list, then we have got a satisfied, right? And what is the recursive step? So basically you have something like, say, X to do that. So you want to check, say, membership, and you want to check the membership of X, and you don't know what is there in the first position, but you know that something there in the first position, you have a tail, and you go on checking whether X is a member of tail, right? Now let us come to another problem, which is partitioning a list on a pivot, right? So what is the thing we want to do? So let's say we have 1, 2, 3, 4, 5, 6, 7, 8, or 9. Now let's say we have this pivot. I want to partition the list into two. One is, say, before, the other is, say, after, right? So how can we visualize this? So we can visualize this as so we have some element X which we want as, so this is our pivot element. And whatever is there before, sorry, X will be there in the before list, and this will be in the after list, right? And this, if we concatenate this, this will give me the entire list. So what concatenation operation that we can perform here? We have written the concatenation operation earlier, right? So conc, we have say before. So I'm fragmenting this into two parts, this and this. Now how do I write the second part? Basically X after, and then this, the result of concatenation should be list, right? Now this will give you instantiate the before and the after, right? Because you know already X, and what is known? What is known is X and known is list, and you have to find out this and this, right? And if we just say that these two are concatenation, this list is a concatenation of these two, then Prolog will taking care of assigning before with this 1, 2, 3, 4, and after with 6, 7, 8, 9. So you might want to check out the program that is written there. I'm not going to execute that. A second variation of this can be, can you give me exactly the before and the after element of a given element? So what I want as output, if we have this input to be 5 and this list, my output would be what is the exactly immediate before element and immediately after element. So again, how do you visualize this? So we visualize this as, I don't care what is there in the beginning. I have before, then X, then after, and I don't care what is happening after. And if we concatenate this, this will give me what? This will give me list. So how do we write this concatenation operation here? So basically you have a don't care, then B, X, A, don't care. This will give you the list, right? So I think with this, let us stop today. Let us try to recapitulate what we have done till now. We have tried to provide the philosophy of Prolog programming, which is basically a goal-oriented programming where we just specify the intent and the rest of the thing will be taken care of the programming environment. But one thing that we need to also make sure that there is also a procedural aspect attached to it or a program while we talk about the efficiency concern as well as decidability concern, right? And finally, we have provided examples of how do we write program with recursion and started to provide the features of the list data structure. And we'll be exploring more on this in the upcoming classes. So till now, I think I'm done for today. If you have any questions or doubt, I'd like to